First, we're going to present a little bit of technical background on software development and testing for multi-core processors. The first question that probably comes up is, why do you need to do this in the first place? So to answer it, we need to go through a couple of fundamentals. Most everyone developing automotive software are familiar with single core processors and used on embedded control modules. It's pretty simple. You've got a central CPU core that executes code. You have an I/O bus to connect it to the outside world. You have caches that are connected to the core, and of course memory. The single core limits the speed at which increasingly complex application software can execute. Adding multiple cores, of course, will increase the output and throughput. One second. So multi-core processors are meant to add core processors, of course, to handle concurrent workloads. Conceptually, the single processor core is extended by adding CPU cores, local memory, and private caches. And then other resources such as the I/O bus, more memory, and caches are added, extended, and shared. This allows the data to be split up and concurrently processed by the multiple cores and reassembled. Of course, there's obvious applications for multi-core processors. They're used in transactional data handling, applications for banking, radar, image processing, and so on. For automotive embedded control modules, it also provides the functional partitioning and load balancing for security functions and functional safety. Multi-core processors are the essential bit for driver assistance systems, autonomous vehicle control functions, and of course V2X interactions. So demand for multi-core processors is driven by the benefits that it provides. So the obvious ones, of course, are lower power consumption, increased processing speeds, increased processing and performance due to concurrent processing on the cores, data security by providing firewalls and memory protection, and isolated critical safety functions, or ASILs, with respect to other functions. And of course, since this is really the state-of-the-art technology that's being promoted across all the different computing platforms, there's decreased pricing and increased availability as more and more of these processors come into the market. So what are the steps in designing software application for multi-core processor? Seasoned engineers will tell you first to ensure that your sequential program is working on a single core processor and establishing this as your golden model. That way you always have a reference to go back to. So in automotive, of course, many of the designs are legacy and they're being ported into multi-core environments. This is especially for embedded control. So when you do that, the first thing you have to do is figure out your architecture. And there's different architectures. There's peer-to-peer architectures for decentralized solutions, pipelined architecture to queue information from one computing process to the next, or you might also have a master-slave architecture to ensure that control is synchronized across all the other components. In addition, you need to consider if you're really parallelizing all of the different threads of execution, so they may be all doing the same kinds of jobs, and you might want to do pure parallel computation on the cores. More significantly, you're probably going to be worried about the concurrency requirements, and this is a little bit different than parallelism. Concurrency usually refers to tasks that look like they operate in parallel, but in fact they're interleaved. The execution steps of each thread might be interleaved with others on different cores. So there's basically a distribution of tasks between the different cores. They look like they're running concurrently, but in fact they're still subject to the tasking provided by the real-time operating system on the single core. So from there, the next part of the architecting is to figure out what kind of partitioning requirements you have, or the isolation between the computing resources. Spatial isolation means that you have code or data of one partition. It can't affect the other partition. Temporal isolation means that one partition can't affect the ability of the other partitions to access a shared resource, like memory or a level 3 cache, an I/O bus, that kind of thing. Partitioning, in effect, decides which core the code should execute in and what kind of resources are required. Assigning the tasks to the partitions is both an art and a science. And sometimes it's a bit more of an art, but at the end of the day, you need to figure out how to make these partitions work together. So what I'm trying to say is that the trade-offs between partitioning decisions, real-time performance needs, worst-case execution times, they should be balanced with each other. And experienced software designers usually do a pretty good job of that, and they make common sense decisions on how to do that. But there's still some challenges, and it really comes to when you talk about functional safety. Why is that? So in ISO 26262, there are additional requirements on a multi-core system. So for those of you that are familiar with ASILs, or automotive safety integrity levels, they're used to calculate the risk of a hardware-software component, the combination of the two in terms of severity or the type and extent of injuries to the driver and passengers, the exposure, that is how often the vehicle is exposed to the hazard, and controllability, which is how much the driver can do something to prevent the injury. Each of these are statistical in nature. So if you look at this table below, at the bottom of this picture, you'll see that different ASILs are associated with different types of functionality and risks. So simple things like a cruise control that just provides some speed control based on a set point, that might be an ASIL A risk. There really isn't too much that can go wrong with that. As you move on up in ASILs, you may have nighttime lighting, loss of a high beam creates more risk to the driver. Airbags, as you go to ASIL level C, you may, one of the things that were first shaked out with airbags is that they would deploy too quickly and hurt the occupants. And since then, many man hours have been put into tuning the firing of they're called squibs, the deployment, the expansion of the airbag, so that it will be the right rate for the weight of the occupant and the rate of impact, or the deceleration. Lastly, if you look at ASIL D requirement, if you're driving a vehicle and the airbag just goes off, you can imagine that's a real critical event and very dangerous and very risky, and folks can definitely get hurt with that. So you can see that with the higher the ASIL, the more important it is to get it right. One next slide here. So getting it right, it includes that the algorithm itself that runs on the core guarantees its processing with hard real-time constraints. In today's architectures, assuming an algorithm has unlimited access to shared resources like the caches or the I/O bus and other resources on the multi-core processor, it's pretty dangerous. Multi-core processors handle multiple functions and simultaneously compete with each other across those resources from each core. This effectively means that the algorithms on each core will interfere with each other and further increase the worst case execution times. And the impacts of this can't be underestimated. So ultimately, especially for higher ASIL applications, software engineers have to determine the worst case execution times for critical functions. And there's three strategies on how you do this. One is, and it's kind of the first strategy, is some folks rely on static tools and software tools that analyze code to estimate the worst case execution time are, they generally are not that accurate. The numerical models that they use, they predict greater interference than there actually is in a real environment. And so they're kind of, the results, they're oversimplified and they're bloated. So these exaggerated worst case execution times don't take into account the software architecture and scheduling. So in general, it's not very accurate to use a static tool. The second approach, which is fairly common, is that some folks extrapolate worst case execution time from single core processor environments and then hope for the best. So what this means is you run some code on a processor, you try to figure out what the basic utilization is, and then you just estimate what it might do in a multi-core processor environment. However, the problem with this is that the shared resource contention in the multi-core system will interfere with each other, and it increases the worst case execution time beyond what you would have seen in the single core processor. And what we've found, and it's very interesting, is that in many cases, the interference is much, much more than the engineers would have predicted. And so that's a risky gamble, especially if you're going to be deploying an ASIL-C and ASIL-D application. So there's a third strategy. So by using analytical methods and benchmarks to determine worst case execution time, you can get a much better idea of what your risks are, especially when you're deploying ASIL-C and ASIL-D applications. So for the next part of our webinar, I'd like to hand over control to our CEO of Rapita Systems, Guillaume Bernat. Guillaume?
Hello, Chris. Thank you. Thank you very much for the very good introduction. My name is Guillaume Bernat. I'm the founder and CEO of Rapita Systems. We've been working on the issue of multi-core timing analysis for quite a very long time. Interestingly enough, maybe 3 or 4 years ago, we kept pushing the message of the need for doing multi-core timing analysis, and we had very little interest. And suddenly, in the last 12 to 18 months, it's just taking the whole industry by storm. So the message that we've been delivering over the years suddenly starts to resonate with the audience. So the question perhaps that we try to address here, that was the main title of the workshop, of the webinar, is how can you use the full power of multi-core processors, making sure that if there are interference because of shared resources, these interferences are identified and they are either avoided or mitigated. And mainly you have, as Chris was trying to say, a engineering reliable number safety factor in which you can put to dimension your systems when there is interference. So that's why the main part of my presentation is. My part of the talk is to go a deep dive into what are the issues that you need to address, what are the challenges for doing interference analysis, and provide some conclusions to the work of how you can provide freedom of interference. I'm sorry to be a bearer of bad news, but if you expected that there would be a magical method to provide freedom from interference and no cost, no effort, I don't believe that solution exists. There are, however, and that is the key take-home message of my part of the talk, is that there are ways to mitigate and quantify what are your potential interference channels, and therefore deal it in a proper engineering manner. So, if you want then to start digging down into the main principles of the timing analysis, and the question we try to address is I try to outline this in 4 main points or principles. As Chris was saying, processors today, multicores, are so complex that not even cheap manufacturers have a completely full understanding of their behavior. And that's why I call the best model of the processor is the processor itself. When life was simple and you had an 8-bit microcontroller that fits in the brain of an engineer, then you can have an accurate model of the processor because things happen as they were supposed to happen, as documented. Processors today have so many parts and components that are complex interactions that trying to model it is I don't want to call it only futile, but a very, very expensive exercise. The second part, therefore, is that if you cannot make a model, you have to do measurements. Therefore, testing and measurements is a fundamental principle of our methodology. Except that measurements alone, repeating the same test a million times, if you're not testing the right thing, is not correct. So for that, what we need to do is to make sure that as part of the hardware selection process, there are observation points, there are channels of information, we call it observability channels, where we can instrument and observe what is the behavior of the software. Some chip manufacturers built in tracing ports and debug interfaces to collect some of that data, but some others don't. So we have to provide alternative mechanisms, and as part of the hardware requirements process, that has to be as part of the hardware requirement specification to make sure that that observability is possible. The third principle, and it's an unfortunate one, but it's a real one, is that what I call you shall trust no one. So first part is keep saying processors, systems, operating systems, platforms where when we observe a behavior, the first reaction is, well, that was not supposed to happen. And you certainly, in the case of an airbag, you don't want to be an airbag deploying too late because suddenly there was an interference on something that was not identified or detected. If you see our role more like an auditor, when you have your finance and your accounting system at the end of the year, you bring some auditors that just check that you've done the absolutely the right thing. And it's basically the same duty. Of course, you've done all the accounts right, but you still need to have someone to audit and to verify that independently that you've done the right things. And the approach to do that is that you need to question every single assumption. So if there is an assumption which is fundamental for your analysis, for your safety argument, that evidence of the assumption needs to be evaluated and provided evidence for. And I have some more details for this later. The other point that quite a few people ask me says, but I'm not interested on this very complex process. The only thing I want is a tool that I press a button and gives me the worst case execution time. Well, I'm sorry to disappoint you, but I don't think there is one. And if you know one, please let me know, because I'll be very, very interested to know that. We've been doing research work for 20 years on this topic, and we still haven't found not even close to a full automatic solution. There is a fundamental part of engineering wisdom that is required to understand what you're trying to do and to analyze the results. The tools, however, do something extremely valuable, which is the automation of the production of data and the collection and analysis of this data, so that the engineers can do what they do best, which is understand and make wise engineering decisions. So to the question of, I want the button solution, the reason one, and if there was, you probably would not like the number that it comes at. So basically that's the same as not being available. So then what is then the problem that we're trying to do? The challenge for moving from single cores to multi-cores is that there are shared resources. The shared resources can be very simple ones, what I call the direct ones. These are direct competition for resources, for example, to access the memory. So when two cores, core A and core B, try to make requests to memory, they share the bus, which is an interconnect in the middle, and when there's traffic on this bus, you get delays. The intermediate or shared caches that also produce delays. Memory as well gets affected if you have to serve requests from different parts of the memory, needs to open and close pages. These are the easy interference channels to understand because we can relate to them. This is almost as if you were traveling from city A to city B on a motorway, and the motorway is empty. Well, the traffic, the time to travel is very nice and comfortable. If there is direct contention because there is other traffic, other cars on the road, you will suffer additional interference. That is easy to visualize. The harder part is identify, especially for the more safety critical systems, what I call the indirect interference channels. And this is where the behavior of a piece of a transaction, of an access to memory or an operation, it's affected from a dependency that is not direct or not obvious, and usually because of the two others. For example, even though a multicore processor, even if it's working, you work alone, and rather have a bus, you have an interconnect. Different requests of memory, because of the status of that interconnect, may follow different paths. These paths may have different execution time. So you are not really competing on the actual channel to go all the way to the memory, but because of a third-party behavior state of the system, the routing algorithm may produce a different path, and that path may have different execution time, for example. There may be variability on memory access latencies just because it's the nature of the hardware itself. But there are even more obscure ones which are known but provide these indirect channels. And one of the key ones, for example, is if there is a shared level, let's say level 2 cache, that even if it's private to three of the members, when a processor is using its own version of the cache, the cache coherency protocol sends messages between the cache controllers to identify which areas of memory needs to be invalidated. So even though you are not sharing any resource, because processor A, for example, core A is using its own area of cache and its own area of memory, and processor B does something completely different, maybe in a separated systems, there is a hidden channel underneath where these comments or these messages can affect the behavior of the cache. The pathological case is when this traffic, and we've done this in some experiments, can completely collapse and block the execution of one cache with factors of execution time of more than 10 times. And these are the kind of issues that we need to try to identify and avoid by design. The third one is what I call the unknown ones, where assumptions which are fundamental for your safety argument are not true because of defects or lack of documentation or designs which were not what I expected. So we did an analysis on the P4080, and we had a very bizarre situation where if you run the same application in core 0 and then the same application in core 1, core 0 was always much faster than core 1. They're doing exactly the same thing with the same inputs and the same outputs. And after investigation, what happened was that the priority on the bus is not fair. It was documented that it was supposed to be fair, but when there were due to requests on the bus, core 0 always won. And when we talked to the chip manufacturers, the system and chip developers, they said, well, that was not supposed to happen, like many others. There are all the very bizarre effects that can depend on the culture of safety and the criticality of the system needs to be addressed. For example, there was a case where the executing of heavily floating point algorithms affected the execution time because the heavy execution of floating point algorithms, the floating point unit overheated when the clock when the CPU overheats. The safety mechanism to lower the clock frequency kicks in, and therefore that slows down the whole system. And again, this is something that was not supposed to happen because the heat dissipation was what's supposed to be the right one. So like this, depending on the level of safety and the level of criticality you want to understand, it could be that Your analysis is to run your application alone and then identify how sensitive it could be to the direct interference channels, or to make sure that you know which direct interference channels are and they're avoided by design. However, you need to be repeating the same things, identifying what are the other interference that can be, plus as well identifying by experiments mainly whether fundamental assumptions are required for the analysis are also hold for multi-core processors on the unknown category. So first, we know, I said before, the first challenge, as I mentioned before, is identifying the interfering channel. So what can go wrong? The second is making sure that the assumptions which are fundamental for your safety argument are correct. Typical argument is, well, I'm going to write my piece of software, and I'm going to use the performance counters on the processor to identify and quantify how many memory access it does and how many of those happen to be cache misses. The performance counters, we found in quite a few number of processors that they may not count the things right or may not count the right things. So if the performance counters are fundamental for your safety argument, specific tests and analysis needs to be performed to verify, to provide quantified certification data that you can trust them. Or at least some of them are the right ones, or the right combinations of those ones that need to be used. Another typical issue we found is that, or a typical question that customers ask is, he said, well, I don't need to do any of these analyses because the real-time operating system will provide temporal isolation. And probably does in one way or the other, except that ultimately you need to provide confidence for yourself that the behavior it is as expected. If your whole safety argument relies on that there exists a mechanism, the operating system that provides a freedom of interference or a temporal isolation, the question is, where is your evidence that this mechanism behaves correctly? The same thing appears, the second comment appears with the use of caches. So typical interference channel is because of sharing of caches. So if you have a shared cache and you have processors that are making requests to the cache, the cache contents of a core may be disrupted because cache evictions are being introduced by memory access coming from a second core. One mechanism to mitigate that is to partition the cache between cores. And let's say, for example, that half of the cache is allocated to one core and the other half of the other cache is allocated to the other core. In an ideal world, that would be it, except that there are side effects where at the lower level, this isolation is not fully guaranteed. And just without trying to go into much detail, there's a special register called the Mises status register, where there's a little buffer that holds the transactions that are in flight from the cache to the memory. This is a single point of failure. All the access to the cache can be partitioned, but not the exit of the cache going all the way to the memory. If one core, one part of the cache collapses that bus or that buffer, the other part of the cache, when it needs to go back to the memory, needs to queue as well. And if that buffer is full, then that blocks the whole system. So these sort of assumptions, where at a high level are very nice and simple, we provide partitioning, therefore we are okay. Our argument is, what is your evidence to verify that the behavior is acting the same way? The typical one is that was not supposed to happen is when particular devices that were supposed to be disabled suddenly generate traffic because they were not really disabled. And for example, generating DMA memory transfers, which disrupt the time of the memory and time of the buses. The final one is addresses the question of the impact of a change. So one of the key issues of multi-core timing analysis is how sensitive is the system to small changes. And the changes we've seen are quite non-linear. It could be that a change in the software because an optimization increases the execution time. You do another change, decreases the execution time by a few percentage. You do another minute change, and that multiplies the execution time by a big factor. Other change has no change at all. So if you understand that changes on the software and changes on the build process do affect the execution time in a non-linear way, and we put a testing strategy around that, it means that when there are changes in the software, you can reduce the amount of testing and verification that is required. So the building block of the safety argument is then understand what are the assumptions which are required to make your arguments and provide evidence of those assumptions. Which then leads to the next one. Sorry, wrong slide. Next one, which is, but how much? So one of the questions we identified here was how to demonstrate freedom and interference, which I would like to rephrase in a different way. Is how can I demonstrate how much interference a particular application can suffer? And if interference is unacceptable because it's a factor of 10, for example, then you know that you have to put some partitioning mechanism and avoidance mechanism in place. If the interference is manageable because that's a small percentage, then, and you can quantify that, then that's acceptable. So the key way, the methodology to do that is to, that we've been proposing over the years, is to start with an analysis method mainly based on measurements, we call hybrid measurement-based approaches, which is a combination of collection of data from an observation of how long pieces of software really take to execute on the hardware with no assumptions about how the model of the processor works, together with some analysis, or the high-level analysis, to understand what is the impact across the whole application. Now, that is easy to do on a single core processor or on a multi-core processor with an application that runs alone. Except that when that application runs alone, and this is the example that we show here on this diagram on the green arrow, you want to be able to have mechanisms to see how sensitive is that application when there is traffic on the other cores. For that, we have a product we call the Rapita, which are interference generators. They are extremely well-crafted pieces of code that hammer specific resources. And there's a full catalog that allows to do interference generations on the bus, on the caches, on the memory, different levels of memory. And the idea is that you are able then to expose a given application to a maximal amount of interference that has been carefully generated. And that gives you an envelope of how sensitive is your application, and therefore answers the question of, is my application sensitive enough? Is it free from interference? And if it has interference, how much that interference can affect my application? There are also different use cases about how these rapid images can be used. One of the typical aspects is to quantification of the hardware architecture. So typical processes, you have two CPUs that you want to select for your process, for your system. Which one is better? Performance average numbers are usually a bad indicator of a worst case behavior. We have some smaller, slower processors, or allegedly with less average performance, but have far less pathological worst case behavior, and there's an argument that they are more suitable for safety critical applications. So how does then the methodology that encompasses and puts all these concepts together work? Okay, we are not inventing, we don't have a magic wand that suddenly is going to be revolutionized and says absolutely, wow, oh, how fantastic the idea, how original it is. It is really a consolidation of wise software engineering practice put in the context of multi-core timing analysis. And we express this into this V model that you see on the screen. So there is one part which is, we call the first part of the process, is understanding the requirements. What are you doing timing analysis for? what are your requirements? Is that you're porting a legacy application from a single core to a multi-core, and as an application has pedigree? Or is that the integration of diverse applications with different levels of pedigree into a single core processor? These issues are quite different. Second part would be to understand. To satisfy those requirements, you need to understand what is the hardware architecture, the software architecture, the structure of the code, the availability of tests, whether the tests are adequate or not, and in particular, this is the level at which you perform the interference channel analysis. First, where are my potential interference? What are the risks if an application uses that interference in a way that is not expected? So the next part is, once you understand what are you doing it and why you're doing it and what are you facing, so the beast of the hardware you try to analyze, then you can carefully design some tests to provide evidence to satisfy these assumptions. And those tests, for example, can be, my application is very highly sensitive, I expect to interference from a particular, for the cache, because of the heavy cache usage. I want to make sure that what would be the potential impact if my application did compete on the cache, assuming that, for example, that cache is not partitioned, or even if it's partitioned. So you design those tests specifically to answer those questions and quantify them. The final part is then, once you have the test plan design review, is then how do you write it down in a way they're executable. And this is the first part of where the tool automation can help. So think about these tools. I'm going to show this later as part of the demo later on, that you write tests to ask those questions like you would write a unit test. I want to run this piece of code against this set of inputs or these configurations and generate the results of the behavior and produce some analysis of those results. And if you write it in a way which is machine understandable, that means that they can be repeated. The final part of the automation then is being able to have a tool chain that takes those tests, running on the targets, collect the data, and then produce the analysis results, which are then, of course, finally go back to the engineering world, engineering wisdom. Somebody needs to make sense. And those results will probably make you scratch your head and say, hold on a second, that was a strange behavior. That was not supposed to happen. What does it mean? So then you need to have a circle going back to ask more questions, for which you have more tests until you get to the bottom of the problem or the issue. And for example, accept that this is an expected behavior, or feedback this into an architectural change that allows them to avoid that hidden interference that has been detected. And then once these activities performed and finalized, then you are ready to summarize all this data, which is the final accomplishment summary of the results of the analysis. So nothing groundbreaking here. We're just formulating a process that is required to achieve that, to present that evidence. The key fundamental part is that one of the most painful parts is how to collect the data. And this is where we have provided an integration of our tools plus custom development specifically to facilitate and automate that process. So the idea then is that the engineers working on this project, the only thing they need to do is to come up with the tests, which are the experiments that you need to run to provide answers to questions that are required for your safety case. These tests are then, using Rapid test tool, run automatically on the target, and these tests configure or use what we call these rapid events to generate a stress on particular parts of the target on a whole range of configurations. And whatever you run on the target then gets analyzed with Rapid Time and Rapid Task, which are our tools for multi-core or single-core timing analysis. And all this data then can be presented and synthesized so that the users can make sense of what it means for you, comparing it with the expected behavior of the tests, and take conclusions for that. We're going to make these slides available for for everybody attending attending the webinar. So I'm just not going through with that. So just to try to summarize my section before we go into the demonstration, what we are doing is multi-core timing analysis is a requirement when to use the power of multi-core processors, which is being driven by the increasing functionality and availability on the market. With great power comes great additional risks, and those risks are the impact on execution time of interfering channels that we don't know. Ideally, you want to provide freedom from interference, providing that is a bit more tricky than it looks. The question is, how can I produce the evidence to show that the interference is either system is free from interference, or is quantified, or is avoided? And that's what we do. So, and I'm just going to pass the token to my colleague, Christos. Christos, as we do, is our multi-core timing specialist, and he's going to do a demonstration of those concepts and principles in operation. Thank you.
Well, we're switching over here. If any of you have any questions that you would like us to address, feel free to use the Q&A bar on the right side of your window. We'd be glad to answer questions.
Thank you very much, Chris. So as part of my demonstration, I will be presenting our demo application, which runs on the NVIDIA Jetson TX2 platform. This platform has two clusters of CPUs. On the first cluster, we have 4 A57 cores. On the second cluster, we have 2 Denver 2 cores, 8 gigabytes of DDR4 RAM, a GPU with 256 CUDA cores. The application itself is an open source artificial neural network, which is written in C and CUDA. We use YOLOv3, which is the object detection and classification application of the SET algorithm, which uses the Darknet framework. The sources for the application itself are available on GitHub quite freely. So the sequence of execution of the application is that when you load it up, it will load the artificial neural network into memory and then pass on to the GPU for processing. Then it will read the input frame by frame. It will run its object detection algorithm, which happens primarily on the GPU. And this is the part that we are analyzing as part of this demo. Also, the next step is calculating the bounding boxes around the items that were identified. Then we draw the output on the screen and we read the next frame, and we continue until we don't get any more frames, or there is a specialized exit condition. So the application that we on the actual target board looks like this. So on one side of the screen, we have the output from the application, which is outputting the results from executing the object detection. On the other side of the screen, we have a timeline of the frames per second as they appear in the system. So when the application itself does not have to compete for resources, it typically runs at just about under 15 frames per second. And we can use the simple user interface, which is also on the screen, to select what kind of contention we would like to add to the system to see the impact. So in this case, we select main memory as our source of contention, and we can see that the frame rate drops from 15 to just about above 10 frames per second. So even with, we can see that there is indeed an impact, and that impact has to be analyzed. So for this demonstration, we have prepared some sample requirements as well as some assumptions to help. We assume that the average execution time that is acceptable for processing one frame is 85 milliseconds. The absolute maximum that we can handle is 150 milliseconds. We also assume that we have test data which is available for testing, and that test data is of good quality. So that's another important aspect that one needs to consider. Also, we have some prior knowledge that other applications in the system may have high memory usage. So the question that we'll try to access is whether our task can miss its deadline when it has to compete for access to the main memory. To do this, the first step that we need to do is to understand the hardware and how the application itself may interfere with it. So a first iteration of this analysis could be that we know that the application is statically mapped onto one of the Denver cores, and we can assume that it will be using the hardware resources which are highlighted in green. So that will be the three fabrics or buses in the system, or the memory controller, the GPU, as well as resources which are available inside the clusters. So based on that view, then we need to think about how would we design tests that give us the information that we need to measure the impact of contention on those resources. So in this slide, we have a much simplified view of the hardware. So the test that I will be demonstrating today has yellow executing on the first Denver core within the Denver cluster. Yellow itself will be using level 1, level 2, the buses, main memory, and the GPU for its processing. And we have rapid daemons on the rest of the cores in the system, which perform a very high number of accesses to main memory by producing many misses in all the levels of cache that are available in the platform. So we've prepared this test, we've run it on the real target, we got our execution trace, and in the end, this all gets processed automatically in a rapid time report, which is on my screen right now. So the tab that I have in front of me, the invocations tab, has a timeline, if you want, on the executions of every invocation of the root function. In this case, the root function is detect in thread. This was executed 1,000 times, which corresponds to 1,000 frames being processed. And we can get some more information about this by, we can, for example, expand individual invocations and see the exact call tree that was observed during specific invocations. More important view is the execution time tab, where we can have a high-level view of the execution time metrics of our application. These are minimum, average, high watermark, and the maximum observed execution times. We get that sort of information for all the functions in the system. There's also the capability of, with fine-grained instrumentation, to be able to dig in and see specific areas of the code that took long time to execute. Another useful thing to understand about the execution of an application is the distribution of execution times. So if I were to zoom in, we can see that we have some small outliers of execution times, but overall the distribution of execution times of our application follows quite a bit closely to a normal distribution, which is quite common effect in complex hardware. The next bit, we have the contribution time. So this tells us which functions contribute the most in the execution of the system overall. So in this case, most of the time is actually being spent in the function could_mm_copy, which indeed is doing the transfers from main memory to the GPU and vice versa. So we are expecting to see quite a bit of increase in the execution time of the application itself, because most of the time is spent using the resources that one of the resources that will be stressing. This is a comparison of executing the system with 0% interference on the main memory, and with the maximum interference we can generate on the main memory. In this case, the average execution time, we can see that it has increased by 122%, whereas the high watermark has increased by 140.2%. The actual execution time here, the average is 83.9 milliseconds. The high watermark has gone up to 104.5 milliseconds. So on average, our system will be, if the system experiences a very high level of contention on the main memory, we can expect that the temporal properties of the system will not meet their average behavior, but the absolute maximum that we can handle is a lot higher. Is within the limits that we'd expect. And then here we have a bit more information about the actual impact that the contention can have on different functions within the system. So the most extreme example, we have 1,330% increase in the execution time spent in the detect and thread function. So the outcome from this is that our application will be missing its average execution time requirement when it has to really compete for hardware resources. However, it should still be within its maximum allowed execution time The next iteration of the loop should be to investigate whether that behavior is acceptable within the context of the system itself. And this is the end of the demo, so I will be passing the mic to Guillaume.
Thank you, Christos. That's been very interesting. Just as a sample of the kind of information that you can display on these type of analysis. The concluding remarks on where we want to go is that the title of the webinar says demonstrating freedom from interference, and that should have come with a little star that says terms and conditions apply. Unless you have done a very, very careful design with lots of restrictions and limitations on how the resources are used, the answer is probably you can't. And I'm sorry, but that's the reality. Multi-core processors are beasts that need to be controlled. We'd like to formulate the question that needs to be asked in a slightly different way. The question is, you can provide evidence that whether there are interference channels and which of these interference channels exist, whether your system is able to avoid by design these interference channels, whether your system is robust. Here robust means robust to changes, and the idea then is how you can develop robustness testing that shows and exposes the systems to different stresses and see how it reacts in a controlled way. And the final question to answer is, let's assume that there is interference. If the interference on the system is bounded and quantified, and you have evidence that you can trust, then you can rely on that evidence. And that informs architectural decisions. We still see some systems where the most cost-effective and guaranteed performance way of using it is to use one core. And it seems very odd to have to leave all the other cores unused, but unless you can tame the beast of the power on the other cores, the amount of interference that they generate doesn't provide the added value. With careful allocation and careful analysis and production of evidence, that power can be unleashed. But that requires two parts fundamental to this. Is one, you cannot replace engineering wisdom. Going back to the point, a tool that just blindly tells you what is the worst case execution time, well, it doesn't exist, and if it existed, you wouldn't really even like the number. So the question here is, what are the architectural changes or architectural decisions that I need to make on my system so that I can, in a cost-effective way, identify what is the potential interference channels that there are, and how can then have a set of tools that can automate our process so that this analysis is cost-effective. There's one question that says, what are the inputs required for the tool to run to generate execution times? And the input is, we look at go back to we remember the picture of the tool. What we need is an environment in which provides a robust set of external tests where the system runs completely on the target. And this is because the argument that you want to make needs to be done on a configuration which is as close to the final configuration that you deployed as possible. It doesn't mean that you cannot do some early estimates on parts of the systems on a representative board, on a demo board, or an open board, or with only parts of the system. But the development of the argument goes from early timing estimates with an approximate system gives you the right order of magnitude, and then as the system evolves and develops, you want to have more accurate pictures in a much more close to the final target, and therefore less deviations from the future behavior. It is. There's a second question that says, does it require instrumentations in software to generate execution timing reports? The answer is not necessarily if there are hardware tracing mechanisms available on chip. Now, So the question is, it depends on what's available on the target. Some chips provide some level of tracing, but at the speed that these modern processors go, even hardware debuggers are really struggling to get enough data, especially where for doing accurate timing analysis, you need to find traces or debug traces that simultaneously trace every single CPU in the system, and that can be quite challenging. So if the system has a on-chip tracing mechanism in place, then we can use it. If not, then we have to go back to another point where you have to provide a level of instrumentation, which can be extremely lightweight. And there's always a trade-off of how deep you analyze your system. So the typical approach is that you start instrumentation at a very high level, let's say a task boundary, provides very little or very high level view of your system, but we know really details all happen inside of each task. And once you understand the behavior, then you can go do that a bit. So the answer then is tracing required? Some level of tracing is required. If there isn't hardware, you can use it. If not, it has to be instrumented. Okay. A few more questions are coming in. It says, did you do test with AutoSAR software? But the answer is no, not yet. We have all the systems that we developed and we analyzed. They haven't been using AutoSAR, but there's no reason why the analysis cannot work with AutoSAR models or AutoSAR software. It's just another architecture of how to do automotive software. So there's another question that says that if we provide S19 files and our AR-XML files, runnable min-max times, this tool can generate execution times? I don't understand your comment of system configuration requirement. The argument is no. The whole point of our methodology is that our tools observe the execution time of whatever is running on your target. And in order to generate the evidence of the interference, what you need to do is you need to run exactly the same tests on the target together with the rapid daemons to generate interference. So we do not make any assumption on model of the processor and trying to speculate on that. Do we need a detailed hardware model as an input to the timing analysis tool, or only source code is required? The answer is only source code is required. We make no assumption of how the hardware works. And this is why the argument we make at the beginning is that static analysis tools that require that hardware model are inaccurate, because that modeling is first very expensive to do, and secondly, well, you shall trust no one, so you shall not even trust the hardware model. So there's a final question, another question that says, is the ACLD project, I assume it means that if the ACLD project has to do code coverage through trace, or can use code instrumentation technique? I would like to think that the question is, can we do collection of data through a trace, or can we use instrumentation? I think that's the same question I asked before. Yes, we can use one or the other. Can we do code coverage or analysis via for microcontrollers boot ROM software also? I don't think there's any issue with that. In the end, software is software that runs, that gets instrumented, provides a trace, and that's enough.